After Napoleon's defeat in 1815, a young Sadi Carnot fled France due to his father's association with the defeated emperor. He moved to Warsaw in 1815 and then to Germany in 1816. While in 1821, Carnot became fascinated with steam engines and began his journey to understand their workings. Carnot's genius lay in the abstract approach he took to understand engines. Rather than focusing on the details, Carnot focused between the heat flow between two thermal reservoirs. Carnot realized that for maximum efficiency, an engine must pass slowly through equilibrium states and be reversible. This theory revolutionized the understanding of modern thermodynamics as well as development of second law. As theorized, Carnot's cycle consists of 4 reversible cycles, 2 adiabatic and 2 isothermal. As shown in a piston cylinder system, first is isothermal compression, piston moving inwards compressing the gas, temperature staying constant at TL and heat removed from the system. Next, adiabatic compression, piston continuing moving inwards, further compressing the gas, temperature increases from TL to TH with no heat transfer occurring. Third is piston moving outwards expanding the gas at isothermal expansion, where temperature remains constant at TH with heat added to the system. And at last, the adiabatic expansion, where piston continues moving outwards and temperature decreases from TH to TL with no heat transfer occurring. And this completes the Carnot cycle. In the figure shown is a PV diagram of Carnot engine. From the theorem proved by Carnot, we know that any reversible engine working between 2 given temperatures all have same efficiency. Now, question may arise that why did Carnot specifically use adiabats and isotherms in his cycle as representation while he could use any other reversible graph as a cycle? To understand this, we need to know from the given schematic of the Carnot engine, in order to achieve the maximum efficiency, the reservoir's temperature should be equal to the temperature of the working fluid in the engine. Because if that's not the case, we could always put another Carnot engine between the reservoir and the working fluid shown, drawing more work that defeats our purpose for the maximum efficiency achieved. Now the next point to note is that heat transfer through a finite temperature difference is always an irreversible process. Now for a thermodynamic cycle undergoing temperature change and heat transfer simultaneously, for the cycle to be reversible, we would require an infinite sequence of constant temperature reservoirs running from starting temperature to the ending temperature along the length of the process, such that at each point the temperature difference between the system and the reservoir is tiny along each step of the process path, so that the heat transfer occurs reversibly. So to get rid of this infinitely many reservoirs and keep the process totally reversible, Carnot geniusly formulated this usage of adiabats and isotherms in a cyclic process. Now coming to the topic of limitations of Carnot engine, in the first case, we see that Carnot's theorem only applies for ideal gases as working fluids. Carnot's original formulation focused solely on the volumetric mechanical work done by the gases, which is only observed in ideal gases. When using a non-ideal or real gas in Carnot cycle, heat is spent on both volumetric mechanical work and chemical work against van der Waals forces, as shown by Joule and Thomson. As a result, the efficiency of the reversible heat engine using a real gas depends on the gas's chemical properties as well as the temperature of the isotherms given. Now coming to the second case, using Carnot cycle as a 2-phase power generation cycle. Heat absorption and rejection at constant temperature can be closely approximated by boiler and condenser in the 2-phase region, and an efficient turbine can produce a reasonable approach to reversible adiabatic expansion, but difficulty occurs in the compression part. If compression is carried out slowly, there will be an equilibrium between the liquid and vapor, but the rate of the power generation will be low and will be an appreciable heat transfer to the surroundings. Meanwhile, rapid compression will result in 2 phases coming to very different temperatures and irreversibilities. Meanwhile, for high efficiency heat addition requires a temperature difference of high level, but above the critical point, which will make the isothermal heat addition difficult.